Welcome to this very broad introduction to network analysis. I will start with a few examples, then I will explain how the force-driven layout algorithms work. Those algorithms are those in charge of placing the data points in the space of the image. So that's what you need, the most important thing you need to understand if you want to read a network map. I will then explain how you should approach reading a network map, and from there how you should approach making a network map. And I will end with a few ideas about how to articulate measurements with visualization when it comes to network analysis. And let me start with how we tend to think of networks in popular culture. What you can see in this slide is a few ways we represent networks in popular culture. I mean, movies like Minority Report, science fiction, and other things. Those are the images you would get in 2020 when I took this screenshot for the query in Google, connecting the dots. And I'm going to show you what it looks like today. So today we have something relatively similar. And I just use this as an entry point to how you may think of networks right now. So something you will find, for example, is that knowledge is more than information because it puts the elements of information in relation with each other, and the difference between knowledge and information would be connecting the dots. And so knowledge as a way of putting certain elements together. The idea is not absurd, but the problem is that navigating a network is more complicated than it looks here. And basically look at those images. So for example, this one, you don't have any edge, any line crossing another line. So this is a very tame, a very simple, very easy network, a very friendly network. And when we tend to represent networks in popular culture, they tend to be like this, not too entangled. This one also is not very much entangled and so on. You would see that, you see that very well in the 2020 picture. So it looks like network visualization. The promise of network visualization is that you could lay knowledge down in an interface where you could have an overview, and then you could click with your fingers. You see that here too, like you see Hans. It's the ability to go and act on the network and find the important bits of information is given to you, and you can navigate complexity that way. The problem with that is once you get a real world network, a real empirical network, it doesn't look like this. It's much more entangled, and it comes with a lot of problems. Essentially, making a network map and reading a network map is about solving those problems of the data being entangled. Just to make this point, let me show you one network that we will see later on. This is an airport connected when there is an airline connecting the two airports. It doesn't look like what you have seen just before. We do have dots and we do have lines, but they are so massively entangled that it has to work differently. I will come back to this example. But before we go to examples of network to work with, let me give you a few examples of networks that have been used in other contexts. I will just start with this picture I took in the office of Dana Diminescu. Basically, she was the head of the research project where Gephi, the network analysis and visualization tool I co-created and that I will show later on, was created. So it was created in the frame of this research project where we were studying migrations, migration communities or diasporas, and their presence on the web. I'm not going to explain the entire research project. It's very interesting and so on, but I don't have the time. And I just want to show you that the way we have worked with networks in this context entails a lot of printing and annotating of the networks. And this is what you can see here, because Dana had taken all the work we had been doing with a network of sociologists and historians and economists working on the question of migrations and about multiple migrations, multiple diasporas of multiple countries. So we have worked with all those people using network visualization as a way to work collectively, as a way to interact with them, as a way to find new questions to explore, as a way to have new hypotheses emerge. So it was a way to do research. It was not just giving us the answer of a pre-existing question, but it was pretty much creating new questions all the time, which is why we had to discuss a lot about what those networks were actually meaning and how to interpret them and what was relevant in them and what was interesting or not interesting. And all that work has been done through these annotations where we have highlighted certain things, try to annotate what is what, and try to put certain networks in relation with each other, and so on and so forth. So network maps can be a good medium for exploring questions alone or in a team. This is maybe one of the oldest network visualization you can find. This is a so-called sociogram from sociologist Jacob Moreno. This is a network of kids, school kids. So it's a classroom, and you have the boys represented by triangles, and you have the girls represented by circles, and you have affinities or acquaintances represented by those lines. So in practice, Moreno went to interview the kids, and he asked them, okay, given the choice, which other kid would you like to sit next to in the classroom? And so kids answered, I would like to sit next to him, next to her, and so on and so forth. And those preferences, those affinities of one kid with another kid were represented with these arrows. So we don't see very well the little points of the arrows, the tip, but they are directional. So this boy said, I want to sit next to this girl. Now, you may have a very simple interpretation of this, which is that the boys are on the one side and the girls on the other side. I want to highlight that it's not just about where we put the triangles and where we put the circles. It's that we see that there are much more connections within the boys or within the girls than from the boys to the girls or vice versa. So we have two, let's say, communities or two clusters, and we can see them with our visual system. We can just see that those two groups are mostly separate. We can actually count how many connections there are from a boy to a girl or vice versa. There's just one. We could call that a bridge. And we can see even more things. So for example, you may have noticed that those two girls are isolated. They are not connected to the rest. I don't know why. Maybe there are an explanation for this. So we see groups that are more connected, groups of nodes, of entities, of items that are more connected with each other than they are with the entities or items or whatever of another group. So groups more connected internally. This is what we will often call clusters or communities. And our ability to see those groups depends on where we put the signs representing our data points. So the triangles on the circles. In the language of network visualization, we call those nodes. So a node is an item, a data point if you want. It represents whatever you want. It could represent a kid, it could represent a company, it could represent a word, whatever things you want to put in connection with each other. So the generic word for those is node. And the connection between the nodes is usually called an edge or a link. And I will use those words, and there are yet other words we could use in mathematics and so on. But let's keep things simple, nodes and edges. So nodes and edges are the elements that belong to the world of network science, and they represent something of the real world most of the time. And yes, we can say nodes and edges so that we can talk about networks in general without having to think every time about what they represent. So here, nodes and edges are kids and preferences between kids. I will go fast on this slide, but I want to show it to you because it represents the kind of networks or the kind of graphs, as we call them sometimes in mathematics, that we had in the 80s and somewhat also in the early 90s. They do not have many nodes and they do not have many links, but they are very rich and they look like diagrams. The key takeaway here is that small networks can be understood by just looking at which boxes are connected to which boxes, which nodes are connected to which nodes. You can actually track the connections individually because you don't have that many, and then you just need to be able to retrace those connections, and then you can spend the time you need to understand what is connected with what, and you can get the information encoded into the network that way. This works because it is small enough, and then you can basically, if you make a diagram like that, prioritize clarity. You can try to make it as clear as possible, and one of the things you would do is to try to have the edges not cross each other and so on. That's why you have the edges that are curved and they go in certain places and so on. Okay. But the networks you will probably have to deal with will look more like something like this one. They are much bigger and they have so many nodes and edges that it is no longer realistic to have them to minimize the crossings between the edges, or just even to have them laid out in a way where you could individually follow each of them. So there is no hope any longer to know exactly which node is connected to which node from the picture. You could have that from an interactive interface. If you are in a software, you could put the mouse on top of a node and know to which other nodes it is connected. But the picture itself, this screenshot, for example, you can't know if a given node is or isn't connected to another given node. What you can know, however, is the trend, the tendency of certain kinds of nodes to be connected with each other. So this is maybe the most famous network visualization ever published in a paper. It's from Lada Adamic and Natalie Glantz, and it represents the blogosphere just before the second George W. Bush election in 2004-2005. So the blogosphere is blogs connected with each other. It's before Twitter, it's before Facebook. So before we have what we call now social media, the politicians would communicate with blogs. And in a blog, you have on the side the so-called blog roll, where you would put links to other blogs that you think are your friends or belonging to relevant to your audience or people you respect and so on. So you choose who you put into your blog roll. Adamic and Glantz collected, harvested these links in the blog rolls, and they assembled the network of political blogs, self-disclosed as liberal in blue or conservative in red. They used a force-driven algorithm to place the nodes in the picture so that when two nodes are connected, they tend to be closer. And what we see is two blobs of dots, of circles. So the blue are the liberal and the red are the conservatives. The blue are on the left and the red are on the right. But what's really key to understand is that the layout algorithm ignores which is which. It doesn't know that a blog is liberal or conservative. It just knows to whom it is connected. And so we have two groups. And it turns out that those groups are the liberals and the conservatives. If you look closely, you will see that there are a few red in the blue and there are a few blue in the red. So we don't know why it is. Is it a mistake? Is these people saying they are conservative while they are liberal? Are those actually conservative and liberal, but they are more connected to the other side for an unknown reason? I don't know. But it's just, the detail is important just to show you that, and this is really crucial, it's not sorting the dots by color. It sorts the dot by connections, and it finds two groups. And then the colors are on top of it. The colors are, in fact, independent of the two groups. So it is very remarkable that basically the color maps each group, and we have a blue group and a red group. The way you interpret this network is to say that the liberal blogs tend to cite liberal blogs and to connect to liberal blogs in the blog role. And conversely, the conservative blogs tend to connect to conservative blogs, but the conservatives tend to not connect to the liberal and vice versa. So we have what is known as homophily or assortativity. Basically, you connect to people who are like you. And that is why the title of the paper is Divided They Blog. Very famous paper that was at the very beginning of network science and computational social science. This paper was so famous that it has kept haunting network science ever since. And you will find in popular culture so many networks that are also part blue, part red, and that are said to illustrate typically the polarization of political life in the USA or other things that would be very polarized. Here is a more recent example. This is from January 6th, 2021, when the Capitol was invaded by partisans of Donald Trump. And Twitter, which was not yet owned by Elon Musk, banned many accounts that called for supporting this insurrection, including that of Donald Trump. And I found this network tweeted. So what you see here is each node, each dot is a Twitter account. They have been identified as the left and the right and coded in blue and red. You have yet another one which is in yellow, which is pro-Trump QAnon activists, as this person names them. And in black you have all the accounts that have been banned following the insurrection in the Capitol. And you can see that we do have a big separation between the blue and the red, which means that also on Twitter, even though it's no longer the blogosphere, the left tends to cite only the left, the right tends to cite only the right, and even within the right, you would have like the far right, who is its own subcluster within the political right. Just before I move on to explain how a network layout algorithm works, let me just acknowledge that there are other approaches to visualizing networks, the most common of which is representing them as matrices. Here you can see two matrices that represent the same network. I'm not going to explain it beyond the fact that the principle here is that nodes are represented by columns and rows. And when the node in a row connects to the node in the column, then the cell of the matrix would be represented in a different color. Here it would be like black, but you could have colors if your connections have weights and so on. The way to read those other visualizations is obviously different, and they are better in certain situations. Typically, if your network is really, really dense, if it has many, many edges, then matrices will be more efficient than dot line diagrams. But I'm not going to open that door, and I will stay focused here on network maps. And now I will just basically explain how the algorithm works. Let me go back to this slide we've seen already. When you have a network where there is a way to place the nodes so that no edge crosses another edge, a simple network as like this one. Basically, we call that network planar. It means we can lay it down nicely. Now, the problem with most networks is that they are not planar. What it means is there is no way you can flatten the network so that you can follow the connections nicely. Think of it like this dress. It has been sewn onto itself in a way that you cannot iron it. No matter what you do, there is no way to put it nice. And in fact, with the most networks we work with, this is so massive that we have to find a different strategy to be able to read the network than just following all of the connections. So basically, the purpose of the layout algorithm is to help us read the network in a different way. Let me first explain how it works, then I will show it to you, and then I will explain why it helps us read networks in a certain way. But first, how it works. It works like a physical simulation. Think of the nodes as little magnets that would repel each other, and think of the links as little spring that would keep the nodes together. So you have two forces in this system, a repulsion force and a spring force, an attraction force. Now, you have the experience of magnets and spring, so you know that two magnets of the same polarity, they repel each other when they are very close, right? So close, you repel strongly. If they are far apart, they don't repel much. You don't even feel the strength of repulsion. The spring works the other way around. When the spring is elongated, it pulls hard, but when the spring is not elongated, it doesn't pull. So you have, if we plot the intensity of the force over the distance between the two nodes, when the nodes are close, so the distance is small, the repulsion here in red is very strong, while the attraction is weak, right? So they repel like magnet, but basically the spring does nothing. On the other hand, if they are very distant, the attraction, like the spring, will be strong and the repulsion will be weak. So because those two forces have to cross each other at some point, it is basically guaranteed that there is an equilibrium. There is a balanced state where the two nodes should find the optimal position where the two forces balance each other. That's the principle in the layout algorithm. So the algorithm computes those strengths, those forces, and runs them iteratively. It's just that if you had just two nodes, you could basically solve the equation and find the distance. But here, because we have the entire system of all the nodes, we just can't solve the equation and find all the distances right away. This is basically impossible. So we have to do an approximation. And that is why it works like a physics simulation. You have to run the numeric simulation to get an answer. And this means that it depends on the starting position. Let me show you now what it looks like. So we are now in Gephi, a network for visualizing networks. And we have opened a network where the layout has already been computed. I just want to show you that we do have nodes and we do have edges. And in this case, they represent airports connected by airlines. And so, as I said, the layout has already been computed once, and you can just remember that you have like the green on the bottom left, and we have the yellow on the bottom right, and we have the purple on top. So what I will do is I will compute the layout again. To do this, I will simply randomize my layout. So now the nodes have been placed in random positions, and now I will run the force-driven simulation. And here we have another rendition of the network. First of all, you can see that it does move, it does run. So we don't jump to the solution. The solution evolves live in front of you, and it reaches a point which is balanced, and we can basically play and stop the simulation. The next thing I want you to notice is that we do have our initial clusters. We have the yellow, the blue-green, and the purple, but they are not in the same position. So we still have the same clusters, but in different positions. Now, let me just run it again. So to do that, I will simply start again with another random position and run the layout again. And once again, we get yet a different version with still the same clusters, but they are once again in a different position. And if you do it again and again, you will have pictures that are different every time, but they are not completely different. You will always have the same clusters, but they will be in different positions. This is because this is not a scatter plot. The axes do not have a specific meaning. It is only the distances that make sense. The algorithm encodes the structure of the network into the distances between the nodes. That is why you have always the same clusters. So the purple end up together, the yellow, red end up together, and the blue-green end up together, because they are these communities that are more strongly connected internally than with the others. But they may end up on the right, on the left, they may be flipped. This depends on the starting conditions on the random positions in the beginning. We could find ways to make this deterministic, so reproducible, so that you have always the same map. But it is more useful to understand that basically what the north, the south, and so on are, they are basically irrelevant in this context. They are arbitrary. You can perfectly, if you want, you can rotate the view. It doesn't change your interpretation. What does change your interpretation is some settings, and I'm not going to go into the details of Gephi and the layout algorithm. We will have the time to see that together another time. But there would be some details that also explain if the clusters are more or less separated and so on and so forth. So you can act on some of the details, but basically the layout guarantees that if you have strong clusters, you will always find them in the same, not in the same place, but the clusters will be the same. So that was how a force-driven algorithm works. It's actually a family of algorithms within which you have multiple choices, and you can find different algorithms, and they will have different properties. Basically, they will always give you the clusters, but not necessarily in the same way. In this example here, you have the same network represented by 3 different force-driven algorithms, the so-called Früchtermann-Reingold on the left, Force Atlas 2 in the middle, and Force Atlas 2 with Linlog, aka just Andreas Nowak's Linlog algorithm on the right. 3 different algorithms made by different people at different times, and they have different properties. The one on the right, the Linlog, is the one known to have the best cluster separation, which is what you want to have in general. So you think of it as the gold standard. That's where we see the clusters best. And I think you can see that in those 3 pictures. They have very different ways of manifesting the clusters visually. And I think that if seeing clusters is what you want, and I contend that it is what you want to do most of the time, then the network on the right is just the best. Now you may just think at this point, okay, so clusters exist in the data structure, in the structure of the network, and the layout makes them visible, but probably we could also compute them and retrieve them with an algorithm. And you would be right, some algorithms do that. They are named community detection or clustering algorithm. Now, the problem is that there is no single definition of clusters, and therefore, when those algorithms give you clusters, you're not sure they are the clusters in the sense you want, which is kind of a complicated question. I just want to mention the question now. I will not open that door, but I will just give you a sense of ways in which there is a discussion about what a cluster is. And let me start with this. This is the divided daylog network that you have seen before. The most natural way you want to divide this network is by the blue ball versus the red ball. They have a different color here, but whatever. one group versus another group, which is one way to split the network. But first of all, there would be another very legit way to do it, which is on the one hand, the highly connected nodes, and on the other hand, the poorly connected nodes. It's also a good way to separate the network into kinds of nodes that have very different properties. Those properties are not being connected internally, but they are more like how many neighbors you have. So this would be, to make an approximation, say the elite blogs, like the influencers versus the more mundane, more normal blogs. They are also kind of two categories that we could retrieve. And yes, some algorithms do that. And now in the real world, communities often overlap. So you don't belong to just one community, you belong to multiple communities. You belong to the group of your friends, you belong to the group of your family, you belong to the group of your colleagues. And so you know how it is. So when you ask a clustering algorithm to put every node into one cluster, it's kind of wrong from the start, because in reality, most nodes will actually belong to multiple clusters. But then we don't really know how to retrieve a structure like this. And it is so complicated that maybe it's not really useful. So yeah, these are ways in which some clustering algorithms give you something, but it is not always the groups that are the most true to the situation. So it also depends on what your network is, what you want to retrieve, and so on and so forth. This is why there are multiple layout algorithms that you can use, and multiple clustering algorithms that you can use. Not explaining here why you should pick one over another, but the reason none has one over the others is because they are useful in different situations. And if you really want to learn that discipline, you would have to understand what is useful and when, and there is an entire literacy about what to use and when. So just in short, the takeaway here is there is not one single layout algorithm that is the best, and there is not one single community detection algorithm that is the best, because they correspond to different situations. And if you learn the literacy of network visualization and analysis, you will learn how they are better in certain circumstances, and so on and so forth, which I'm not going to teach you now, but just know that it exists, and that's why it's an expertise you could acquire. Let me propose you a few steps to approach how to make and analyze your own network maps. It's like a recipe that is relatively universal, and it's like a good starting point for you to have a direction in this process. So here are the steps. I am going to illustrate them, but in short, you will start by applying a layout, identifying the main clusters, identifying the main structural holes, I will explain, then similarly subclusters and minor clusters. Then you will put colors on the node, and you will compare how the color distributes over the different clusters you have identified. And then you will look into spatial nodes. So you will move from looking at clusters to looking at spatial nodes and spatial edges. And finally, you will name and describe the clusters with actual names. Those are the steps. They will make more sense as we go through them. So here is an illustrated example. So when you start with your network, it has neither color nor layout. The first thing you will do is to apply a good layout. I could ask you where you see the clusters in this example. Let me just mention that we have a bunch of nodes that are around. This is fairly common. So those nodes that are like making a ring around the central component of the network, they are disconnected nodes. So because they are attached to no other nodes, they don't really know where to go. For the rest of this example, I will just remove them. That's a decision that we could discuss. But I'm going to do that now. And we may agree that we do see the clusters in a certain way. And I'm going to go with ABC. So just for the record, so this is a real world example, and the analysis has been done by someone who is not me a while ago, She's a researcher named Deborah, and she was studying the Rio Plus 20 conference on the web. So the nodes are websites about Rio Plus 20, and the connections are hyperlinks. So we know what kind of nodes, what kind of network it is, but we don't know the structure. And she was documenting her own process of visual network analysis. And she had made the choice to identify those 3 clusters. So I'm not saying it's the absolute truth. I'm just saying she decided to go with those 3 clusters. And at this stage, we don't know what they are. And so we just give them a letter, right? So this is not a good way to communicate your network, but we are working on it. So temporarily, we will give them letters to identify them. And the question is, what are they? So yeah, we went for those 3 clusters. So she surrounded them with potatoes. And then we can also identify the structural holes. So the holes are the areas of the network that are empty or relatively empty of nodes. Just mind that we have a lot of lines. So this is not a hole in terms of lines. So we have a few lines, a few connections here, but they are still holes because they are between the clusters. If we didn't have those holes, those spaces, we could not identify the clusters as clusters. So that's what I mean here by structural holes. Inter-cluster emptiness, right? So you have those different structural holes and you have a big hole in the middle. Why do I ask to identify the structural holes? Because they are good things to interpret. The same way when we have, let me go back to the previous step, the same way we have A, B, and C, and this leads to questions such as, why are the nodes within A together? Why are the nodes between B together and C together? What makes them more connected with each other than with the nodes in another cluster? So that's a question we could ask about the clusters. We also have questions about the structural holes. Why are there not many nodes that are connected to A and C, or many bridges between A and C? And why are there almost no nodes that are connected to A, B, and C? Why does it look like it should be either or? So identifying the holes is also useful to analyze the network. So now that we have identified the clusters and the holes, we can, if we have the time, push the analysis further or the description further by finding the subclusters. And we could also go into analyzing the minor clusters. I would be saying like, what is this mini cluster? What is that mini cluster? And so on and so forth. At this point, you may wonder whether this is not being too subjective, because not only the layout is different every time we run it, but also the way you draw those potatoes is different from one another. So we will maybe not identify the same clusters. This is true, but only to some extent, because there are a lot of things in this process that we will actually agree on. For example, the fact that we have one bigger cluster that is called A here, we will always find it. And we may disagree on where the cluster is, but we will always agree that there is a bigger cluster. The same way, if you do the divided day blog network, you will always agree that it has 2 big clusters. And it doesn't matter if they are on top or on the bottom, if it's flip or turned, the relative sizes of the clusters will be consistent, right? So this is objective knowledge, even though the details will vary from one time to another. The good analogy here is we can discuss where the Mont Blanc starts, where is the valley and where is the mountain. There is no obvious boundary for the Mont Blanc, and we could discuss if it's there or here. But the fact that the Mont Blanc exists is not up for discussion. It certainly does exist, and it's a little bit the same. This cluster exists here and it is big, and we don't know exactly. There would be different ways to draw the potato and to decide what's in and what's out. And whatever way you pick is not the absolute truth, because really this is more like a spectrum. But nevertheless, this will be one big cluster. Now, once we go further down the process, we will have reasons to sharpen our description. But the important point I want to make here, the takeaway, is that if you don't go through this stage of naming the clusters and the subclusters, there is no way to progress. So it's just better to commit to an imperfect description and move on into the analysis, even though further down the line, we may just actually change our categories depending on other things we find. So the next step in the process is, assuming that we have attributes describing our nodes, is to use those attributes to put colors on the network. So what you see here is the researcher who produced that network. She manually coded the kind of website they are, depending on the content in the website and how they present themselves. She found 4 categories plus others that she named social ecology, green economy, deep ecology, and new ecologism. And you can see a little bit like for Divided Day blog that some of the clusters, each cluster is dominated by one color. It's not an absolute rule, but you can see that here on top, the cluster A is mostly red, so mostly social ecology, and this one is mostly green economy, and this one is mostly deep ecology. So we could be moving towards naming the clusters after their content. We could say, okay, A is the social ecology cluster, and B is in fact the green economy cluster, and so on. If you want to communicate your network to a reader, you may rather use explicit names like those than ABC. Now, this was one layer of coding, but you can also have other layers of description of your nodes. If you think of your nodes as a table, it may have multiple columns. So here's another columns we have in this data, which is the language of the website. So as Rio is in Brazil, the local websites are in Portuguese, the international websites tend to be in English or multilingual, and then you have a few other languages like French and Spanish. And what you see here is that the social ecology, the cluster A, is not just defined by its content, it's also defined by its language. So if we had named it social ecology, it's not really untrue, but it is not the totality of the truth, because it's actually not just website about social ecology, but also local websites in Portuguese. So there are different ways the colors are mapped to the clusters. Another interesting way you can see here, and which is fairly common, is that the colors have made subclusters appear. If you remember in this cluster, the cluster B, let me just go back in the slides. Deborah had not identified subclusters in B, which I understand why. It's not very clear that there is a divide anywhere. But now, if we look at the language, we have on top English. We tend to have more English-speaking websites, while at the bottom we tend to have more like multilingual websites. And in fact, if we look more closely, we will realize that they are actually 2 different kinds of websites. They are different kinds of international institutions, and all the United Nations related institutions are those in green. So the fact that they are multilingual is because they are those these international institutions. The only takeaway I want to make here is once we start to explain the clusters with the attributes of the nodes, it may lead us to create new subclusters to explain and possibly also remove other subclusters. So for example here, I don't know what this subcluster is here on the left, but it doesn't look like different in any way from this other subcluster. So maybe, do we have anything to say? Maybe, maybe not. It depends on everyone, but I'm just saying the process is always ongoing and it's always iterative, and the categories that you end up using in your analysis will be shaped by the interactions between the attributes that describe your nodes and edges and the layout. Now we have kind of a good description of what the clusters are, and the step you would have after this would be to look into whatever nodes are in a specific situation. And then there are many things you may have to say, but basically, first you could ask who is central, so who is in the middle and who is connected to first everybody. So is there a node that is connected to everybody? Not really, but I would still say there is a little node here in the middle that is the only node connected to A, B, and C. So I wonder what that is. Actually, it's the website Nature. I know it, so it's a very famous website. Maybe I have something to say about this. Then you could also look at who is central within each cluster. So for example, who is that node here that has so many connections with other social ecology websites? So maybe it's a website that is important to that topic. So central nodes within the clusters, but also bridges. So bridges would be kind of the contrary. They would be nodes that connect distinct clusters with each other. And you have a bunch of them. But most nodes are not bridges, but when you have bridges, it's interesting. So who is this guy? Who are those two guys? Who is this guy? And so on and so forth. And you may also focus on off-topic nodes. And I mean here the nodes that are off-color, the outliers in terms of attributes. So here we have, for example, a green economy node within the social ecology cluster. Why? Why are they different, and why are they not connected to the other green economy website that tend to be here? I'm not saying it's right, but I'm saying maybe it's interesting to study. So anomalies of all sorts. And then we would, once we have made all these descriptions and once we have iteratively sharpened our understanding of the network, then we would actually give names to the clusters. So the cluster A, for example, which we know is at the same time on the topic of social ecology and Portuguese-speaking website, we may use a name like local social ecology websites, right? Local because it relates to the fact that they are in Portuguese, and social ecology is related to their content. So whatever is useful for you to explain what is going on. That would be the different step of the process of making a network map while exploring it. Okay, I know it's been a long lecture. I just want to create a connection in your mind between how we compute certain metrics with the network and how we visualize them. So I'm not going to go into the details, but I'm just going to show you where you can find this connection between computation and the visual so that you can navigate network visualization also as a tool that could lead to measuring your data in ways that are less subjective. And you will find the link somewhere down below or in this course to this PDF that is an appendix to a paper we published in the Digital Humanities Conference in 2019 with Martin Grandjean. Our presentation, our paper was called Translating Networks, but I'm sharing the appendix because that's where you have like practical material that can help you. And basically, the idea is first to remark that the nodes that you can compute as having certain properties, distinct properties, they will sometimes be in different places of your network. And I'm not going to go into the details, but let's say the simplest way you have seen that already, is that if you're a bridge, so you will be between the clusters, this corresponds to the betweenness centrality. Whatever the name, but just remember, if you compute the betweenness centrality, it will most often give you allow you to detect the bridges. And conversely, if you want to find the nodes that are within that are central within a cluster, you may go for example, degree centrality or number of triangles here, whilst other metrics like the page rank will give you nodes that are more central at the scale of the entire network. You will find some details if you keep scrolling through this presentation. Basically, here we are. You will find a number of slides where properties can be related to metrics you can compute. So, for example, if you want to analyze the size of the graph, you could count the number of nodes, the number of edges, but you could also look at the density. And the density is often, so it's a metric you will find in, for example, Gephi. It will give you a number, but you can interpret it as complexity or completeness of the network. So those would be global properties. I'm moving on. But you will also find local properties. So for example, the degree, which means the number of neighbors of a node, we will interpret it as connectivity or having many neighbors, while the betweenness will tell you that you are the node that have a high betweenness centrality are often the bridges, but they have other meaning in sociology, for example, such as the concept of broker and so on. And on the contrary, closeness will be more like the center or the middle node in the network, and so on and so forth. So you can just go through this and look at the different connections between statistics that you can compute in a software like Gephi, and where you could look at them and how you could interpret them in your visual network analysis. And I think I am just going to stop here.